So we did number 1 together, which is on drawing a card. So suppose that a single card is selected from a standard 52 card deck. What is the probability that the card drawn is a king? And Rebecca, what'd you get for that one? Both. Perfect. So there are 4 kings out of the 52 cards, and so we get 1 out of 52. Part B, I apologize, was worded poorly. So it should read this, okay? It should say, now suppose that a single card is drawn from a standard 52 card deck, but we're told that the card drawn is a face card. Did the knowledge that the card is a face card change the probability that the card was a king? Okay. Sorry about that, because with the heart there instead of the face card, it got pretty confusing, right? So now let's just tackle this with face cards. So by knowing it's a face card, what is that? It does change it. And what does it change in our fraction? So we had 4 out of 52 before. What does it become? Close. 4 out of 12. What changes is our denominator, because it's no longer out of the whole deck, because I'm telling you it's a face card. And there are 12 face cards. So now we're only looking at 12 cards instead of 52. And out of those 12 face cards, we want a king. And there are 4 kings out of the 12. And so then you can reduce that to 1/3. So what term is used to describe this kind of thing? This is what we call conditional probability. Because the probability changed based on something happening, right? I knew that the card was a face card, so therefore it changed what we're working with. Okay, number 4. Jane and Juan have invented a card game. From a standard deck of cards, a hand of 3 cards is dealt. It's a winning hand if exactly 2 of the 3 cards are the same suit. How many winning hands are there? So this is not a probability question. It's a counting question, right? And so I just put it in here just to remind you, okay, we got to still work on that counting. And also we're talking about cards here, right? And these are some card problems. So what are some things that we need to try or consider? What are some things that maybe you tried or considered? Yeah. Okay, good. So the number of cards changes each time you're picking one. Did anybody try this one? Anybody get Chase?
That is cards we multiply. So first I have to do the immediate cards.
So we get pick any card, 52 cards, right? And then?
And then there's 12 other ones in the same suit.
Okay, so 12 because we want it to match the suit, so same suit. Does that make sense to you guys? So say he picked a heart. Well, how many more hearts are there? So he needs to match the same suit. So he wants his first 2 cards to match the suit, right? And then times. So not a heart. So there are 3 other suits out there. There's the diamonds, and there's 13 of those. There's the 13 clubs, and there's the 13 spades. And together there's 39 total. And so then so that would count that up. 24,336. Oops. Put 63 instead of 36. So 336. All right. And so have we considered all the ways by doing that? Question on that? So do we have to consider, here's my question, do we have to consider this? So this way we had two of the same suits, so it's like AA and then something different, right? Do we have to consider this case? Or is that considered, is that part of the 24,336? I guess that's my question. Is part of it? Why? The combination? Or is it a permutation? Combination or permutation or so here we're saying how many choices do we have? 52 choices times 12 times 39. But we're also those numbers came from we wanted the first two to match, right? But would it be okay if the first and the last matched? So I'm thinking we have to consider that too, right? So there's 24,336 ways to get that. But we have three other cases we need to look at. And it turns out you're going to get the same numbers, the 52 times 12 and 39 in different orders for those as well. And you can walk through them. And so we need to do one more thing, multiply by 3. So times 3, and we have a calculator on hand? Yeah. That wouldn't work because it says exactly 2, and that word exactly is saying hey, you can't have 3. You gotta have exactly 2. 72,008? Huh? Sorry, 73,008. Like that? Okay. All right. So you did getting to the 24,336, that's like 90% of the work, and that's awesome. That you were able to think through that, get the 52, the 12, and the 39. That's awesome. But we just got to consider, well, it could also happen in a different order. 5, if you draw 2 cards randomly from a standard deck, what's the probability that you get 2 of a kind? Whether 2 kings or 2 sevens or 2 something. Okay. So does it matter what your first card is? It matters what your second card is, right? So you can pick any card, doesn't matter. And so really what you want to find is, this is equivalent to asking, what's the probability that my second card matches my first card? In terms of, not suit, but in terms of value or face value, right? So you pick a card, and how many cards are left in the deck? 51 left. And you're holding a card, and you want to match it. How many other cards are in the deck that match your card? Here's your answer. Okay. There's a 3 out of 51 chance that that second card will match your first card. Okay. Number 6. Probability you have randomly drawn. Suppose you have randomly drawn a 6, 7, 9, and a 10 from a standard deck of cards. What's the probability your next will be an 8? So you're trying to get it straight, right? You're trying to get all the numbers in a row, and you like that 8. And so what's the denominator going to be? It's going to be out of 48 cards because you already have 4 cards, right? And you want an 8. So what's the numerator going to be? 4, because there's 4 8s in that deck. And then we reduce that, you get 1 out of 20. No, 1 out of 12. Okay. We did 7. Number 8 is very similar to number 5. Question? Oh, what do you get if you go 12 over 51? What does it give me as a decimal? Is it 0.2313? Okay, so we need to correct that. So that's 23. Are you checking that? Does he get 0.2313? No. 2352. That's different. Check it again, Chase. Is it working now? Okay. All right, we'll check this. Okay, so 8 says you got 2 people. They select one card. Each select one card from a standard playing cards. Which of the following is closest to the probability that their cards match? So that's actually the same answer, right? It's the same problem as number 5. You guys see that? And so the answer is going to be 3 out of 51. And then what is that as a decimal? Or as a percent? Was it? Roughly 6%. Okay. Number 9, select one card at random from a standard deck of 52 cards. What's the probability the chosen card is an ace or a face card? Okay. So you're selecting one card. What should our denominator originally be? How many are we picking out of? 52. And then we count how many aces are there? 4. And how many face cards are there? And are we counting any cards twice when we add the 4 and the 12? No. They're mutually exclusive. So we got 16 out of 52, which is 4 out of 13. Okay. So then I left this for you to read, right, and try out. And some of you may have been a little intimidated, but let me kind of summarize some of the key points I want you to take out of this. Okay, so, and I'm going to build off of this tree diagram. So with a tree diagram, say we have 2 events. We can have event A can happen or it may not. And then if A happens, event B may happen or it may not. And if event A does not happen, event B can happen or it may not. So there's 4 different routes that you can take when you have 2 different events. The first route would qualify as A and B happening. See both of them. The second route would qualify as A and not B. This would be not A and B. And this one would be not A and not B. And this is another way to represent our Venn diagram. Remember we had our Venn diagram. We've done this a few times. And if this is the first circle represents A and the second one represents B, what do we call this in between? This would be the intersection. This would be A and B, right? But what would this be? This would be A and not B. And this one would be not A and B. And out here would be not A and not B. And so you have those 4 spots in the Venn diagram, the same 4 destinations that you can have in your tree diagram, right? And then you could, I'm not going to take the time to do this, but you could also fill out those 4 spots in the table and have the same 4, right? And so those are the 4 key things with 2 events. Now, from the Venn diagram, so I want to make that connection, but I also want to point something else out. So if we're looking at B, okay, just the circle B. Circle B is created by two different sections, right? And so we could say that event B is the same as everything in the intersection, A intersect B, plus what else? What's the second part? Not A plus B. Sorry, not and. Not A intersect B. Right? Because those are the two spots that create that full circle. So you're either in B and you're in A, or you're in B and you're not in A. Right? If you're in B, you're in one or the other. Making sense? A little bit? And so these are the connections that we're going to make when we work through these problems. But before we do, let's review a couple things. What is the formula for the probability of B given A? We went over this yesterday. It's a fraction. What goes on top? And what goes on the bottom? Here's the picture. The picture, if you look at the Venn diagram, it's the best picture we can say or use. This is saying, what's the probability of B, or that you're in circle B, given that I tell you you're in circle A. Okay, so the denominator is, we're in A. So if you just look at circle A, which part is also in B? A and B. So this is the probability of A and B over the probability of A. So that's one formula we got to remember and be able to use. And then from that, you can solve for the probability of A and B. So we get the probability A and B. It's the probability of A times the probability of B given A. If we switch our A's and our B's, we get this. We get an equivalent expression. Probability. It's also equal to probability of B times the probability of A given B if we need that one. So you can use either one, but that's some key things that we need. So let's bring those to number 10. Okay, so number 10, we have two events, sun or no sun. So let's let A represent sun, A prime no sun, and grew or did not grow. So B will be that it grew, B prime will be that it did not grow, B prime. Okay, so I'm just defining these letters. So find the probability that it grew given that there was no sun. So I'll just use A and B here. But so that'd be the probability of grew, the probability of B given that there's no sun. So A prime. Okay. And well, what do we know about that? That's the probability. We could actually just read that in our diagram. So what it's saying is that we have no sun. So which route are we taking? Bottom route. Okay. So we have no sun. We've already gone so far. We've already gone this far right here. So now that we're there, what's the probability that that it grew? 15%. So there's no math required here. It's just kind of reading that notation. Yeah. Well, it already tells you there's no sun. So that's what the given. So you've already traveled far. You already know there's no sun. So it's not asking could it happen, could it not? Because you already know it did not happen. There was no sun, but we don't know if it grew or not. Yeah. On B, it grew given no sun. That right there, that's a symbol which represents given. It's a third symbol. So we have three symbols now. We got to think about and, or, and given. And the given is that it's not something that's unknown. It's something that's known already. So we don't factor it in as unknown. So, but B is asking now, what's the probability that the plant was in the sun and that it grew? So we don't know either. So this is the probability. I'll just use grew and no sun. So grew and no sun. So now it's an and problem. Well, that's the probability. And I get to choose. Do I want to say the probability that it grew times the probability that it... So there's two options. Yeah, there's too much writing. I'm going to use A and B. It's the same thing. We defined it. So I have two choices. I could do probability of A and B is equal to the probability of A times the probability of B given A. Or I could say it's the probability of B times the probability of A given B. One of these choices is hard. One of them is easy. Okay. If I try the first one, can I get the probability of A happening? What is it? What's right here? Probability to get sun? 0.35. Okay, so now the next one is probability that we get B given A. So we've already traveled to A. What's the probability we get to B? A. Okay, so that one's pretty doable. And what do we get? What's 0.35 times 0.8? 0.28. Okay. Now if we try the other one, what's the probability of B? I have no idea. Because I don't know what happened. Did we get to A or B or A or not A? And so this one falls apart in this problem. And in other problems it'll be nice, but in this one it's falling apart. Now could we figure it out? Yes, but it's a challenging problem, more challenging problem to find out. And I'll show you how to do that because we're going to have to do that in 11. Okay, next one. Find the probability that we get sun given that it did not grow. So this would be probability of A given B prime. And what's our formula? The probability of what over the probability of what? So what's going to go on the bottom? B prime. So whatever's here, whatever's after the given is what goes on the bottom. It's out of that. And then what goes on top? A and B prime. Okay. So what makes it helpful here is this. So A and B prime we can follow that path. So it goes A and B prime. And so we can find that probability. By multiplying together the 0.35 and the 0.2. And we get 0.07. Check me on my math. Am I right? Or is it 007? What's that? 0.07? 0.7. Well, 35 times 2 is 70. And you got 3 decimals, so it'd be 0.07. Okay. So then, so we got the top part, 0.07. But the bottom part, there's that probability of B prime. And it's not so obvious, right? Did not grow. And so here's the idea. If I drew a circle that represents B prime, and here's a circle that represents A, B prime's made of 2 parts. How would I define those 2 parts? The one in the middle is A intersect B prime, right? But then there's one more. What's this one right here? It's not an A, and it's not an B, right? And so those, see, I can't consider B by itself, but I can consider these because that's how our diagram's drawn. And I have the first one, A intersect B prime. We did that. So let's find the other one, A prime intersect B prime. So if I follow that route, we end up here. And so that probability of A prime intersect B prime would be 0.65 times 0.85.